Good morning, my dear students. Welcome to the chemistry class. Today we will continue the last part of these DNA block elements, and today we will discuss the actinoid series. Okay. Here these are also called 5f series. Okay, because the last electron enters into the 5f orbital. The 15 elements from the atomic number 89 to 103. Okay, they are called actinoids. The name is taken from the first member, that is actinium. Okay, and here actually the 8 electrons are successively filled up. Okay, and the elements where the last electrons enters into the 5f, okay, 5f orbitals of n-2 main cell, okay, they are known as 5 block or 5f block elements or actinoids. Okay, and here thorium to lawrencium are called actinoids actually. Okay, but now all the 15 elements, okay, 15 elements of the actinoid series, okay, are considered as actinoids. Okay, that means all the 15 elements including actinium we are considering as actinoids because their physical and chemical properties are same. And if you look at the electronic configuration, then you can understand that half fill and full fill f orbital, that is F7, F14 will be very much stable. Okay, and we know that half fill and full fill orbital are stable because of the symmetry criterion, and that is high spin exchange energy. Now we discuss the electronic configuration. If you look at the actinium, here the electronic configuration is radon 5f0 6d1 7s2, and then thorium, that is the radon 5f0 6d 2 and 7s2, and then protactinium Pa 91 and radon 5f2 6d1 7s2, uranium 92, radon 5f3 6d1 7s2, then neptunium, okay, Np 93, radon 5f4 6d1 7s2, plutonium Pu 94, radon 5f6 6d0 7s2, americium Am 95, radon 5f7 6d0 7s2. Okay, and next is curium. Curium is radon 5f7 6d1 7s2. Here you see that because 5f7 is very stable electronic configuration, so here it is not 5f8. Okay, electrons are going d orbital. Okay, next berkelium Bk 97, radon 5f9 6d0 7s2. Again here is anomalous electronic configuration. Then californium 5f10 6d0 7s2. Then einsteinium Es, radon 5f11 6d0 7s2. fermium, okay, radon 5f12 6d0 7s2. Then mendelevium, okay, radon 5f13 6d0 7s2. Then nobelium, NO, radon 5f14 6d0 7s2. Then lawrencium, radon 5f14 6d1 7s2. Okay, so there are some anomalous is there electronic configuration there that you have to remember. Here you see that americium, okay, electronic configuration is very stable because 5f7 is there. Curium also electronic configuration is very much stable, and that 5f14 electronic configurations like nobelium and lawrencium, they are very much stable. That you have to keep in mind. Okay, next we will go to the oxidation state. In case of actinoids, they generally showing that +3 oxidation state, that is the most common oxidation state, but the range of oxidation will be +2 to +7. In case of lanthanides, the maximum oxidation state was +4, but here it is +7. Okay, greater range of oxidation state is because of the fact that 5f, 6d and 7s, these orbitals have similar, that means comparable energy. Their energy is almost near about same. Okay, and for actinium, showing, okay, +3, and thorium, protoactinium, all that means from actinium to lawrencium, all are showing +3 oxidation state, that is the common oxidation state. Then from thorium to berkelium, okay, that is thorium to berkelium, they are showing +4 oxidation state, and from protoactinium to americium, they will show +5 oxidation state, and uranium to americium, they will show +6 oxidation state, and only neptunium and plutonium will show +7 oxidation state. So the oxidation state first increases up to the middle element, okay, then decreases, okay, that you have to keep in mind. So here the maximum or highest possible oxidation state is +7. And next we will discuss the radii, okay. In the ionic radii of M3+ ions, actinoids elements decreases gradually from left to right in the actinoid series. This is called actinoid contraction, like lanthanoid contraction, okay. Now what is the cause of this actinoid contraction? Same, okay, that is the cause of the actinoid contraction is because of the pore shielding effect of 5 electrons, okay, or 5 orbitals, okay, and due to its as well as due to its more diffuse shape. Actually we have already drawn the structure of s orbital, then p orbital, then d and f. D orbitals are double dumbbell shaped, okay, and F orbital may be triple dumbbell, and more complicated structure is there. And when you are going to the 5f, okay, definitely its orbital will be more diffuse, and because of this it will show the actinoid contraction, okay, and here the contraction is regular, okay. Next we will go to the color of ions. Actinoids ions are generally colored, and the color arises because of FF electronic transition. Uranium 4+, okay, it will show blue color. Uranium 3+ will show red color. Neptunium 3+ will show blue color. So they are showing colors, okay. And if we consider them, their melting point and boiling point, they have high melting point or boiling point like the lanthanides. If we consider their ionization enthalpy, the actinoids have low ionization enthalpy. Next, if we consider the radioactivity, in the previous, that means in lanthanoid, there was only one radioactive element, that is called promethium, okay. But in case of this actinium, all elements are radioactive, but their half-life varies, okay. There some will be for few minutes and maximum to some days, okay. That means their half-life is very small, okay. Next one very important thing is given in your syllabus, that you have to compare the similarity and difference of these actinides and lanthanides. So first we will discuss the similarities. Both exhibits +3 oxidation state, okay. Actually in case of lanthanides you have shown up to +4, but +3 is there, here also +3 is there, so you can tell that one similarity is both can exhibit +3 oxidation state. Both are electropositive and possesses high reactivity, okay, and both form colored ions, okay, because of the FF transitions. And next we can tell both having the same number of unpaired electrons and possesses quite similar spectra, okay. And next we can tell both show magnetic properties, okay, and like lanthanoid contraction, okay, there will be actinoid contraction also, okay. These are the similarities. Next we will discuss the difference. Now first difference, we can tell that in case of lanthanoids, the binding energy of 4f electrons are higher, but in case of actinoids, the binding energy of 5f electrons are lower, okay. Except promethium, lanthanoids are non-radioactive, okay, but all actinoids are radioactive, okay. Lanthanoids have poor tendency to form complexes, but most of the actinoids halides form complexes with alkali metal halides, okay. Next, lanthanum maximum oxidation state is +4, but in case of actinoids maximum oxidation state will be +7. 4f, next in case of lanthanides, okay, 4f electrons have greater shielding effect than 5f, but in case of actinoids 5f electrons, okay, have poor shielding effect than 4f. Next, lanthanoids compounds are less basic. Next, actinoid compounds are more basic. Lanthanoids do not form oxocation, but actinoids there are many oxocations. Like we can tell you that UO2 plus 2, okay. I am writing UO2 plus 2, okay, and UO, okay, that is oxygen. Uranium, oxygen, okay, UO plus, like this, okay. So again I am telling that lanthanoids do not show or do not form oxocations, but actinoids form oxocations. So in this way we have completed your syllabus, okay, that is the D block and A block element, okay. So today up to this, and if you have any confusion or any question, you can interact with me in the live class. So thank you for watching.